For centuries, humanity has sought order, a grand cosmic clockwork where every gear turns with unwavering precision, every event a direct consequence of what came before. We built our understanding of the universe on the bedrock of predictability, believing that with enough information, the future could be known, meticulously mapped, and perfectly foretold. But what if that bedrock is an illusion? What if, at the very heart of existence, where matter and energy dance at their most fundamental level, the universe isn't a clockwork at all, but a game of chance, a cosmic roll of the dice, where outcomes are not predetermined, but genuinely, inexplicably random. This is the paradox, the profound, unsettling dilemma at the core of quantum physics, the riddle of true randomness. Our journey begins in the familiar territory of classical physics, a realm largely defined by the towering intellect of Isaac Newton. In this world, the universe operates like a colossal, intricate machine. Every particle, every force, every interaction adheres to strict, deterministic laws. Imagine a game of billiards. If you know the precise mass, velocity, spin, and angle of every ball, along with the friction of the table, you can, in principle, predict the exact trajectory and final resting place of every single ball after a strike. There is no ambiguity, no inherent uncertainty. The future state of the system is entirely determined by its present state. This concept, known as determinism, became the philosophical backbone of science. It suggested that, if we could gather enough data about the universe at any given moment, we could predict its entire future down to the smallest detail. From the majestic sweep of galaxies to the delicate flutter of a butterfly's wing, everything was, in essence, predetermined. Yet, as the 20th century dawned, this elegant, predictable edifice began to crack. Scientists delving into the microscopic world of atoms and subatomic particles encountered phenomena that simply refused to obey the established classical rules. The first tremor came from Max Planck in 1900. Trying to explain the radiation emitted by hot object, he made a radical proposal. Energy wasn't continuous like a ramp, but came in discrete, indivisible packets or quanta. It was like discovering that money only existed in whole dollar bills, never fractions of a cent. This seemingly abstract idea was soon bolstered by Albert Einstein, who used Planck's quanta to explain the photoelectric effect, demonstrating that light, too, behaved as if made of individual particles, which he called photons. The continuous, wave-like nature of light, so fundamental to classical physics, now had a particle counterpart. Niels Bohr then applied this quantum idea to the atom itself. He proposed that electrons didn't orbit the nucleus like planets around a sun, but occupied specific, quantized energy levels. They could jump between these levels, absorbing or emitting discrete packets of energy, but could not exist in space between. These quantum leaps were instantaneous, unobservable transitions. They hinted at a world where things didn't move smoothly, but blinked from one state to another, defying our classical intuition and planting the first seeds of genuine unpredictability. The true departure from determinism arrived with the realization that quantum entities possess a baffling dual nature. Particles could behave like waves, and waves could behave like particles. Consider the famous double-slit experiment. If you fire electrons one by one at a barrier with two slits and place a detector screen behind it, you'd expect to see two distinct bands of hits, like bullets passing through. But instead, you see an interference pattern characteristic of waves. A single electron somehow passes through both slits simultaneously, interfering with itself. Even more astonishing, if you try to observe which slit the electron goes through, the wave pattern collapses. The electron suddenly behaves like a particle, choosing one slit, and the interference pattern vanishes. The act of observation fundamentally changes the reality being observed. This profound disturbance by observation led Werner Heisenberg to one of quantum mechanics' most unsettling truths, the uncertainty principle. It states that you cannot simultaneously know, with perfect precision certain pairs of properties of a quantum particle. For example, you cannot precisely know W both an electron's position and its momentum at the same time. The more accurately you measure one, the less accurately you can know the other. This isn't a limitation of our instruments, but a fundamental property of the universe. It's not that we can't measure them both, it's that they don't simultaneously possess definite values. The electron is at a specific point with a specific momentum. It exists as a probability distribution until measure ed, and when measured, the outcome is inherently, irreducibly random. This is where the classical dream of perfect predictability truly shatters. If outcomes are truly uncertain until measured, then probability becomes not just a tool for dealing with our ignorance, but a fundamental description of reality. Before observation, a quantum particle exists in a superposition of all its possible states simultaneously. Erwin Schrödinger famously illustrated this with his thought experiment: a cat sealed in a box with a vial of poison, rigged to be released by the decay of a single radioactive atom. Since the atom's decay is a quantum event, unpredictable until measured, the atom exists in a superposition of decayed and undecayed states. Therefore, according to the standard interpretation, the cat is simultaneously both alive and dead until the box is opened and the system is observed. This idea of superposition, where reality is a blurred tapestry of possibilities until observation forces it to choose, is central to the quantum randomness dilemma. But what is observation? And is the randomness truly fundamental, or merely a reflection of a deeper, hidden determinism? The most widely accepted framework, the Copenhagen interpretation, embraces this inherent randomness. It posits that quantum particles exist as probability waves, described by the Schrödinger equation. When an observation or measurement is made, this wave function collapses, and one of the possible outcomes is realized purely by chance. There's no deeper mechanism, no hidden variable guiding the the universe simply rolls the dice. This means the universe, at its most fundamental level, is fundamentally unpredictable. However, this idea of true randomness and the collapse of reality deeply troubled many, including Einstein, who famously declared, "God does not play dice." This led to alternative interpretations, proposed by Hugh Everett. The Many-Worlds interpretation suggests there is no collapse. Instead, time a quantum measurement is made, the universe splits into multiple parallel universes, each representing a different possible outcome. In one universe, the cat is alive; in another, it is dead. From this perspective, randomness is an illusion. From within a single branch, all possibilities are realized somewhere. Other theories, like David Bohm's pilot wave theory, propose that there are hidden variables underlying deterministic properties that we simply cannot access. If we knew these variables, the apparent randomness would vanish, revealing a deterministic universe. These theories preserve determinism but introduce an unobservable layer of reality. The randomness dilemma isn't just a philosophical debate, it has profound implications for our understanding of reality, technology, and even free will. One of quantum mechanics' most bizarre phenomena is entanglement. Two entangled particles, no matter how far apart, remain connected in such a way that measuring the state of one instantaneously influences the state of the other. Their random outcomes are correlated. John Bell's theorem and subsequent experiments have shown that these correlations cannot be explained by any local hidden variables. His strongly suggests that the randomness isn't due to our ignorance, but is an intrinsic feature of nature. The ability of quantum systems to exist in multiple states simultaneously and to produce truly random outcomes is not just a curiosity, it's a resource. Quantum computers harness superposition and entanglement to perform calculations far beyond classical machines. True randomness is also critical for secure quantum cryptography, where the inherent unpredictability of quantum states ensures unhackable e-communication. If the universe is fundamentally random at its core, what does that mean for our concepts of cause and effect? Does it imply that free will, rather than being an illusion in a deterministic universe, might actually have a genuine, non-deterministic basis in the quantum fluctuations of our brains. The quantum randomness dilemma forces us to confront the very fabric of reality, challenging our most deeply held assumptions about order, predictability, and the nature of existence itself. From the predictable clockwork of Newton to the probabilistic dice rolls of the quantum realm, our understanding of the universe has undergone a radical transformation. The randomness dilemma in quantum physics is not just a scientific puzzle, it's a profound philosophical challenge. Is the universe fundamentally indeterminate, a place where genuine chance shapes reality at its deepest level? Or is there an even deeper, more complex order yet to be uncovered, a hidden score to the cosmic symphony that we are only beginning to decipher? The answer remains elusive, a frontier of human knowledge where science, philosophy, and imagination converge. But one thing is certain: the quest to understand the true nature of randomness will continue to push the boundaries of our comprehension, reminding us that the universe, in all its perplexity and glory, is far stranger and perhaps far more wondrous than we could ever have imagined. Thank you for watching our video. Don't forget to like and subscribe. We value your thoughts greatly. Let us know in the comments.